Okay, so hi everybody, my name is Marek. And I'll try to keep my presentation below the time because there's like a lot of going on. And I'm basically representing, I'm talking about the work that we are doing for the last few months with people here. And I put plenty of different notes, requests, and questions to the modelers community. So let me basically start. Before I begin, I have to say, in 2019, it was said that galaxy supernova will happen in 2025-26. This is when we were in Japan, in Fukuoka. So I'm just bringing this up. Some people are in the room here. So it's like either this year or next year. Okay, and the more serious stuff, I would just like spice the discussion with a question. Can the modelers scoop some of the LVK results? And here I just give some personal opinion. So what I mean, if we have a public event, if we have a detection of gravitational waves, then you will know publicly what is the duration of that, what is the central frequency, what is the kind of like how strong is the signal, what is basically the central time, then the sky location. So question is what you can do with all this information. For example, in this plot, we have basically like partially detected signal for O'Connor couch waveform that is at high frequency and like very, very short. And it's also like detected signal is pretty weak. So then if you have neutrino information that will not be probably available publicly, you know it's like somewhere between like 10th of millisecond, as John said. If this happening, the gravitational wave signal is happening 300 milliseconds later, what actually tell you about your waveform? So I'm just like putting here this question because I believe that there are certain information that can be extracted. And this is something that I would like to have this type of discussion of. Yeah, we detect we provide certain information, what we can say right away, and what we can say like later. So after that, let me go quickly to the results and the conclusions. This plot basically shows our constraints on the gravitational wave energy, and then when we can reach the realistic models. In between, we have these numerical models, like on a more extreme side. So we are like 1 or 2 orders of magnitude away. So I just put a request that, yeah, it's like while we are waiting for the detection, how feasible is to have such extreme models to start like constraining them over time while we are waiting for the detection. Then what I was trying to do with my group is to have the physical inference from a collapse supernova detection that basically just like happens automatically, same as what we have for the compact binaries. So at the moment, we have a lot of human involvement in order to have the physical inference. So it takes like yeah, when a galaxy supernova happens, everybody will be just running the algorithm. So it's like a matter of like days, weeks, a month, wherever the computing resources are available, when people are not awake, where people are awake. And I would like to see whether it's possible to do it like within like minutes. So implement low latency parameter estimation using the methods that they already exist. And in this plot, actually, Ewald Müller makes really, really nice catalog of papers with gravitational waves. And I divided them into those related to like pure theory, like pure theoretical prediction, and then some data analysis methods like parameter estimation, detectability, searches, all that sorts of stuff that involves the gravitational wave data. And you can see that when we have 2D models, we had a huge spike of papers that died out. And now we are like in the range when we have these three-dimensional models. And you can see that the interest for like data analysis is increasing, and specifically for physical inference papers, it's also increasing. So let's take some of these models that are available already and rewrite them into a low latency operation. And we are right here, like at this symposium. So this is also tells me that this actually meeting is actually perfect moment overall for the field. And let me give a brief overview of what I was doing with my group. If we divide gravitational wave features, there's like few of them: core collapse, prompt convection, high frequency feature, G mode, F mode, SASI, convection, the memory, the black hole formation. So I selected prompt convection, high frequency feature, and SASI, and try to understand how quickly we can get, how accurately we can get information about this to extract physical parameters from these features. And it's something that I will show is not easy. So we talk about physical inference, but I want to like highlight physical inference versus parameter estimation. Parameter estimation. We were trying to define the parameters where we can assign a number. So say, when is the beginning of the prompt convection? How strong is the prompt convection? Can we distinguish whether we have, what equation of states we have? And that applies to prompt convection, high frequency features, SASI, black hole formation. Basically, every feature depends on the equation of state. Speed of sound, stalling of the shock, energy, source orientation, and even more like compactness, angular rotation, the rotation axis, time of the black hole formation. So putting all of these basically possibilities into parameters that we can quantify. So let me start from the first project. This is what Sophia was presenting yesterday, the prompt convection region. The prompt convection region is pretty weak, and we took basically the first 100 milliseconds, and we were like measuring properties, like what is the central frequency of that for like a few different models. We thank Bernard Müller for like answering our questions. And we have a request. If we have prompt convection, can we have neutrino data to have like the timing? It's like within like 10 milliseconds. Can we have it this data to start like seeing whether this is detectable? Because at the moment it's a pretty weak feature. Then can we have also the evolution of the shock, like data for the evolution of the shock to compare with if we can reconstruct it? When does the prompt convection starts in and ends in your simulation? And I know that this question like came up like already a few times. If we start with a spherically symmetric progenitor, if we have a more realistic scenario, what amplitudes we can get for the prompt convection? Then the high frequency feature, it has a lot of attention in the literature, and thanks to Alejandro Torres Forne and Pablo for helping us with our questions. We basically at the first approximation is basically fitting the straight line to the high frequency feature, we have questions like how does it correlate with is there any correlation with the neutrinos? If we have neutrino data, can we do something together? When in your simulation the high frequency feature starts and maybe ends. Is it possible to get the data of the proto-neutron star radius and mass so we can try to reconstruct it? And is it really the first feature that we'll detect? Because when I look at the waveforms, it's not that obvious to me. Then SASI. SASI is this sloshing oscillation mode of the shock. And Vincent and Miriam have a nice presentation about that. And we have the request, can we get also the neutrino light curves? If there is SASI and oscillation in that light curves, is it possible to get it? What is the beginning and the end of SASI from your simulations? We have SASI and convection. Like, what's the difference of them? SASI is basically a very, very narrow band. Convection is like more broadband, but is it possible to get like more details, like to distinguish them a little bit better? And what are some of the physical properties that we can distinguish them in the low frequency? So yeah, like this convection, or is there anything else? Can we like separate them? Then we tried to understand when the high frequency feature begins, when this convective movement begins, and this is what Pavel has a poster. So question is it possible to have data where we can map gravitational waves to this convective movement? What is actually the beginning of this convection in your simulation? Because like we see our waveform is like, oh, it's somewhere here, but does it correspond to reality? How strong is from convection? Find the minimum peak frequencies. So that's like another thing. If we, in one of these results, we try to basically do like different interpolations to get this time. If we have, for example, prompt convection that is like very, very weak, then we are less precise. So the question is, how strong is the prompt convection? Will be strong convection in a realistic case. Okay, then we also had got the data, and thanks Daniel Murphy for answering our questions. Depending on where the gravitational wave is coming from, is it possible to like combine these different different 6 regions where the data is coming from to distinguish like different regions? So the best we could. So we have region from 0 to 6. 0 is like in the middle, 6 is outside. And then it's possible, like we were combining region number 1 and 2 and 3 and 4. And we are trying to distinguish whether whether we can distinguish it when we have the total wave moment. The answer is at the moment no. But also, like if you have in your data the time when say F mod in region, sorry, the G mode in region 1 and 2 and F mode in region 3 and 4. Maybe I'm mixing, but when the dominant emission is switching, is it possible to get this timing as well? Then we're trying to estimate the energy, the total energy of gravitational waves. And there's also like a poster from Prato. So like, is it possible to get the rotation axis evolution? What is the maximum? What does it mean that in certain direction the gravitational wave emission is the strongest? And we have like an example of how this emission, like the maximum energy emission, evolves over time. And then finally, we are trying to create a web page with gravitational wave sound from Supernova. So, feel free to send us some pictures or movies from your simulation that we can maybe like also show it. And also the representation of gravitational waves. Some groups, majority of the groups provide quadruple data, but then some of the groups provide Newman-Person notation, and we try to like map the tools like to go from one to the other. So that's the question: is it possible to like unify it within the simulation community, and or maybe like use one preferred? Yeah, like I would like to hear the opinion. So, in a summary, having one parameter estimation code that for a supernova is actually challenging. There is I try to show all these questions that we have, and having just waveforms is not enough for us, especially having the neutrino data when we know the timing. So feedback from you will be basically essential for us. So thank you.
So we're time for questions. The other thing I also wanted to say is that now you organize why you understand why the organizers decide to have a whole afternoon empty, because that's the amount of time it take to try to answer all the questions that Marek brought up. But I hope that beside a couple of questions now, people will take the time to talk with Marek so we can keep track of the opinions, because there's a lot of important information we would like to share. I think Jade has the first question.
Hi, Marek.
And then Vartanian.
So that you said that you would like the mass and radius. So I get emails quite often for people asking me for my proton neutron star mass and radius, and I can very easily give you those, and we're very happy to share those, and we can share other things like the shock radius or whatever properties you want, and I'm sure that's true for everyone else with the simulations as well.
Yeah, that would be nice. Yeah.
Yeah. To echo Jade's sentiment, I don't have a question. I have an answer. The answer is yes.
Okay.
We can share with you the shock radii, the PNS radii, neutrinos, neutrino data, energies, luminosities, gravitational wave data. Just list it, and we have dozens of 3D models for all of these, and maybe 100 for 2D, but that's probably not as valuable.
Nice.
Okay, so also to answer this, I will trade you for the full LVK data. No, we can provide all this data, but what would be really helpful is that if you just put together a list, that is, okay, I took some pictures of your slides, but just put together a list of what you want. And some of these things, I think it's a bit difficult to provide, honestly, some of the things you ask for. But yeah, more than happy to share. And if you have some kind of things that you want, we can provide most of these things that you asked for. And then my question, would you want 2D data, or do you prefer only from 3D? Because I have a bunch of 2D simulations.
So that's like, so even if we have a lot of data, like we see if we can actually process all of it. But I would actually start from like the simpler cases, maybe like 3D. Yeah, like it would be nice to have them in the repository for people to use. But yeah, like maybe like at least like starting from like simple lightweight 3D data for like the first pass.
But so like from 3D simulations as opposed to from 2D simulations.
Yeah, but that's actually like question to you, how useful would it be? If you say it's useful, then we would take it.
Yeah, so that's my question to you. How useful would it be to have 2D simulation data for you, or would you prefer the 3D data?
Depending on like what we'll do for the analysis, like how well we can reconstruct the parameters. So that's like maybe like yeah.
So sorry, Jay, I'm just going to grab the mic here and then turn it to you. So we can answer all the questions that you've laid out there very straightforwardly. And of course, it's going to vary model to model and across groups, et cetera. The other thing, I just want to add another layer. There is, of course, a time and place for the you versus us situation, right? You're collecting a lot of data from all over the world, and you have questions, and throwing them back and forth is totally fine. But in my experience, there's another level, and that's the level of working together, shoulder to shoulder. It's not you versus us at all. And
Oh, no, no,
want,
no.
yeah.
no.
So I want us to get away from that language, because I think there's nothing to replace the working together. I mean, just here, in these few days, the amount of information exchange that has occurred between the modelers and the observers, if you will, is enormous, and I don't think this, you versus us and throwing things back and forth over the fence, however efficiently we do this with websites and whatnot, is going to be able to really be it alone and replace that. I mean, really working very closely together is going to be essential as well.
Oh, absolutely. Yeah. I don't want to make it like two sides, like we have to be together. At the moment, there is this situation of having like LIGO Virgo and yeah, people who are outside, but
Kagra.
and like Kagra. Yes.
Okay.
Yeah.
Jay, do you have a
Mhm.
follow-up, or should we move to the last presentation? Okay, so, I think Pablo maybe.
Mm-hmm.
No, thank you for the presentation. So no, I will just want to make the shopping list my own as well, because I liked it, and everything that you said, essentially, I would like to have it too. So I think it's more, and I think many other people in this room. So I think it's more like, I mean, it would be nice to share it with someone in particular, one-to-one, but also to make it public certain things, at least in certain time scale, in the same way that as the LBK is making all the data available and public in certain time scale. So I think it's fair to ask the same to the modelers, at least part of the data of the simulations. I mean, basic things like, I think, gravitational waves, luminosities, mass, radius versus time, and these kind of things. If not the whole simulation, of course, but yeah.
Okay, let's thank Marek again.
Yeah. Thank you.
And